Alrighty, welcome back everybody. It's your main math man, Mr. Shen, coming to you live from Summit Academy. In this video, we're working on doing some probability and statistics practice. And so I'll go through some of these problems, kind of reviewing what we talked about and kind of summarizing it all together. So in the first part, it says Juan and his roommates roll a six-sided die, numbered 1 through 6, to determine who drives them to work each week. It says Juan is assigned the number 5. Juan runs a simulation of rolling the six-sided die to represent the next 20 weeks. The table shows the simulation data. So it says results from six-sided die and a simulation of 20 die rolls. So this is what they got when they rolled the die 20 times. So just recorded and made a table. So in part A, it says calculate the theoretical probability that Juan will have to drive them to work. So when you're calculating theoretical probability, you just talk about what is the possible outcomes. So for example, when I think of a six-sided die, the possible, like I can list the possible outcomes. And I can say it's going to be, let's say it could be 1, it could be 2, 3, 4, 5, and 6. So those are going to be the possible outcomes for this. Then we can say, well, when I'm thinking about the theoretical probability, I would say probability of rolling a 5 would be equal to the number of favorable, or let's actually say the number of 5s divided by total number of sides, meaning how many sides does it have in total. So I would just count and I would say, well, there's 1 5 out of the 6 possible sides. And if I wanted to change that to a decimal, I would say that's going to be 0.16 with a 6 repeating, which is about 16%. All right, moving on. Then it says, for part B, it says, according to the simulation, what is the experimental probability that Juan will have to clean the house? Or it should say drive to work. Let me actually fix that. It should say drive to work. I think that's what it said before, right? Yeah. So, what it's talking about when it says experimental, all it's just saying is what actually happened already. So when you think about the results, it's just listing the table out that you have here. So what we have to say, same kind of setup, we're going to say probability of a 5 is the number of 5s divided by the total number. What I mean by that is how many total times did it happen? Well, what we can do is we can kind of circle the number of 5s. So I have one here, one there, another one here, and another one there. So those are the 4 times, I'm going to say 4 times out of the total, which is 20 rolls. So I'd say divided by 20. Again, I can make that into from a fraction to a decimal. So I'm going to divide that out. I should get 0.2, which is the same as 20%. Moving on to part C now, it says how does the simulation compare to the theoretical probability? So it's just asking what is this, how do you compare the theoretical probability to the experimental? Well, we can, again, just write those two values that we had. So we said the theoretical was 16%, and the simulation, or the experimental, was equal to 20%. So if I wanted to summarize that really simply, I'm saying compare, I have to, talk about the value. So I'm going to say the theoretical probability is less than, because if I'm comparing them, I'm saying, well, the 20 is going, or sorry, excuse me, the 16 is going to be less than the 20%. So I say is less than the simulation probability. Probability. There it is. Messed up too much. Probability. There we go. Sorry about that. All right. Again, if you want to write experimental instead of the simulation, that's also fine. Again, either of those words are interchangeable. All right. And then the last part, for part D, it says if one ran multiple 20-week simulations, should he expect the simulation result to be the same? And explain your answer. So we're going to say the results will be different. One should expect the results of the simulation to get closer to the theoretical probability of 16%. So what that just means is, let me actually say of 16% as they do more rolls. More trials, more experiments, more simulations. Actually, let me say simulations instead, as they do more simulations. Because all we're just saying, as you can record data, for example, you could record flipping a coin, whether it's heads or tails, and you can be scattered on the first, however many rolls you do or however many flips you do. But as you do more and more and more, the data that you record will get closer and closer to the theoretical probability. That's just true for any of those situations. All right. So now, different part now, or different question. Talk about probability of scoring a basket. So now we have to kind of create those simulations, and we have to kind of make those from scratch. So for the first one, it says this. It says probability for Mr. Shank to score in basketball is 40%. Then it says describe how to create a simulation to represent 25 throws. Just want to get my notes for this one. All right. So what we're going to say in this is as follows. We're going to say a couple sentences. So we're going to talk about, how could we come up with a situation where we don't actually have to, sit there and shoot 25 shots, or we don't have to sit there and play basketball for 25 throws. What we can do is we can use a 10-sided die and then do the dice roll instead. So that way it would be a little bit faster. So we can say it like this. We can say, in my simulation, I have a 10-sided die. Again, since they're 10-sided, the results would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are the possible results for that die. And we could say if let me actually label that too. Let's say possible outcomes. Again, an outcome is just a possible result. And then it says if the die comes up 1 through 4. So that would be 1, 2, 3, or 4. Then we could say, then Mr. Shank, that's me, scores. Okay. Then we could say, then if the die comes up as a 5 through a 10, I'm just saying 5, 6, 7, 8, 9, or 10, any of those possible ones. Let me say then Mr. Shank misses the score or misses the basket. Then we could say we also have to make sure we're talking about this important number right here, 25, because we're talking about 25 throws. So we would just say this. We would just say to represent, we represent 25 throws or shots. We would say I would roll the die 25 times. So it's really simple, but all we're just saying is how could we create something where we could get this kind of data, or so that way we could record our data. So we're just trying to come up with how to create the simulation. So no calculation yet, just kind of coming up and trying to build this situation. Then it says, in the next part, it says part B, in your simulation, how would you determine if Mr. Shank has 5 or more successful scores in a row? So we could say to see if Mr. Shank makes 5 in a row, we can say, actually try to make a colon there. We can say if I roll 1 through 4, and we say 5 times in a row, we can say that simulates, try to write that S again, that simulates Mr. Shank making 5 in a row. So what it's asking you for this is, how does that translate if I was to make 5 baskets or shoot 5 shots and they all go in? What does that look like in your simulation? Well, we would say if I roll the dice and it lands on a 1, 2, 3, or 4, if it lands on any of those sides 5 times in a row, then we would say, hey, that's the same as making 5 shots in a row. So really simple on that front side, really easy to kind of piece together. Then on the back, a couple different things going on here, but I'm going to read it off one piece at a time. All right, so on the next part, it says a company is trying to raise tadpoles in different methods. They want to figure out what proportion of tadpoles survive when being fed mosquitoes. There are 100 total tadpoles they used to create this data. So, couple different parts. It might seem really complicated because you see a bunch of numbers, but all we have to look at is for this first part, we're going to say, hey, what is the proportion or what is the mean proportion of mosquito-fed tadpoles that survived as a percent? So this is really easy because all we have to do is just look at this table sum that's down here, because that will give us our percent already. So we're going to say it's just exactly here. Or we're going to say it's going to be, let's say, use table sum. We're going to say it's going to be 14.1%. That's going to be that mean proportion of tadpoles that survived. Now let's actually talk about the data here. So in part B, it says what are the upper and lower 5% bounds of the sample-to-sample variability. So what this is just talking about is this. I'm going to write the directions down here for you. So we're going to say find two values at the border, spell that right, border, then add together, and divide by 2. All right, so what we are looking for, and I'll do two sets of numbers here, but we're going to say the lower bound is this box right here because this has the lowest 5 numbers. So I'm going to label this as lower. And then I can say, well, that means that on the opposite direction, this is going to be our upper bound. And so those are the top 5 numbers at each side. But I'm looking for that border amount. So I'm looking for that border amount. So what I do is I say, okay, well, here's the 2 numbers that are on the border for the lower bound. And here are the 2 numbers, include that color, there we go. Here are the 2 numbers that are on the border for the upper bound. And what we have to do is, like I said, add them together and divide by 2. So let's do one piece at a time here. So I'm going to do the lower bound. So I'm going to label lower. And I'm going to say, all right, let me take those 2 numbers. So I have negative 0.02 plus a negative 0.01. Add them together, divide by 2. What this ends up being is negative 0.015. So that's going to be the lower 5% bound. And what that means is it's saying that, hey, that's where anything below that is going to be the bottom 5% or the bottom 5 values. Same idea, let's do the upper. And so I'm going to look at these 2 numbers. So I say 0.29 and add together to 0.30 and divide it by 2. That gives us, again, use that Desmos calculator, but that gives us 0.295. We're going to say that is our upper 5% bound. So again, it's really simple to calculate this, but it might be confusing at first. But I can assure you it's really simple, just kind of looking at those different numbers. All right, so now we're going to take those numbers and we're going to take what we found from part B, which was this part here, and we're going to take that and combine it with our answer from part A to figure out what we need for part C. So in part C, it says predict the proportion of tadpoles that survive in percent in the whole population and give the margin of error. So first what we're going to say is use answer from part A, which was that 14.1%. And what we're going to do then is we're going to say after that, let me change colors here. We're going to say find range by taking the difference between the 2 answers, from part B. Taking those 2 answers for part B and divide it by 2. All right, so what I mean by is this. So let's go back to our last one. We said one of our answers was negative 0.015, and our other answer is 0.295. So I'm going to write those down. I have purple for this one, so I'm going to say, all right, I take negative 0.015. I'm going to say minus, because I need to take a difference. I take a difference, and I say minus the other number, which is that 0.295. I need to divide it by 2 because I need to figure out what the margin of error is. So I'm going to say divide by 2. All together, this is going to be equal to 0.155. Then it said to put it into a percent, so I'm going to multiply by 100 to change to percent. So I take 0.155 times 100. I'm going to say that's equal to 15.5%. All right. Notice how I haven't circled anything because I haven't found my answer yet. We have to put these pieces together. So now that we found the margin of error, we're going to say, okay, we're going to add that to the mean. So we're going to say our final answer, we'll do in blue down here, I'm going to say my final answer is going to be this number along with this number. So I'm going to say altogether our answer is going to be 14.1%. And then since it goes in two different directions, we have to say if we add it or if we subtract it, so that we're going to have that plus or minus symbol, and then we say 15.5%, which is a pretty decent amount of change there, margin of error, but we can say this is going to be our answer. So that makes sense too, because again, that kind of talks about how the numbers go in the negatives if we subtracted, but also goes up to, past 29 because we're talking about that average survival rate. So make sure you see each of those parts, ask questions if you have any, and as always, super slam that subscribe button.